background notation. So whenever we write any research article on cryptography or cybersecurity, we have to use some notation. And then there is a table of notation. Okay, so if we use any non-traditional notation, so we have to explicitly mention in the table of notation. So if we use any terminologies that is your own, so we have to define it. It's like basic terminology. If I say plain text, non-cybersecurity people, they don't know what is plain text. So we have to explicitly explain what is plain text, cyber text, etc. So basic terminology is background notation. Then we see some cryptography techniques, cryptanalysis, type of algorithms, and good cipher. So these are the some few lecture outline. Okay, what is cryptography? The definition: a secret manner of writing, either by arbitrary character, by using letters or characters in other than the ordinary sense, or by other methods intelligible only to those processing the key. Okay, this is basic definition. Okay, cryptography, what is secret writing? It is the strongest tool for controlling against many kind of security threats. Definition, so later we'll see. So for introduction, transformation of information into an encrypted version form that cannot be read by a third party. Okay. If you see, we write password, so it's a static. Okay. Originally used almost exclusively for diplomatic and military communication. Initially, 1940s, 1950s. Okay. Fundamental change in recent days due to public commercial use of IT-based communication. Okay, may be applied to data communication or stored information. So this is cryptography. I designed this for the whole lecture. Right? For instance, we have Alice, the sender, and the Bob, a receiver. Okay, if Alice have some data to send, we call this plain text, PT. It's a notation, it's a terminology. So we apply some encryption algorithm. Okay. We get the ciphertext. Okay. And then the ciphertext is sent using insecure channel. It's online. Okay, we send the data. Okay. And then others partner, the receiver, they receive the ciphertext. We apply some decryption algorithm and we get the plain text, and the Bob receive the data. This is very simple mechanism. From here till transforming plain text into ciphertext is cryptography. Okay. Transforming plain text to ciphertext or ciphertext to plain text is a cryptography. Okay. And if we plan to see, the attacker need to see what's going on online. So it's using cryptanalysis, anything, using network analyzer or any method to reveal the truth, okay, to reveal the keys. So this is insecure, we call this cryptanalysis. This is the value for the attacker. Okay. So we call this cryptanalysis, this part. And the whole study of cryptography and cryptanalysis, we call this cryptology. Once we have plain text, we need to transform this plain text into ciphertext. We need to apply with some algorithm. Okay. Later we'll see some baseline algorithm. Okay. This is ciphertext is basically encrypted version of plain text. We get the ciphertext. How we know this notation. On the other side, plain text is basically once we decrypt the ciphertext, we get the plain text. Okay. Or plain text is the decryption of ciphertext or decryption of this is ciphertext, so encrypted version of plain text. So this is equivalent. So there must be some algorithm to encrypt the data. Okay. Or there must be some algorithm to decrypt the data. Okay. To encrypt and decrypt, there must be some key Either it's a key, a physical key, or some passwords, or some mechanism like if I give maybe like for example, let us see if we encrypt and decrypt using the same key, same method, same mechanism, we call this symmetric encryption. If we encrypt the data with different key, decrypt the data with different key, asymmetric encryption. Okay, so now we move on. Plain text is a readable message or data which will be used by the cryptographic process. Ciphertext is the unreadable message or data, okay, which is the outcome of cryptographic process. Two different key procedure, two different key produce two different ciphertexts. Okay, encryption is the process of turning plain text into ciphertext. Use encryption algorithm. Decryption is the process of turning ciphertext into plain text. Refer to my diagram. Cryptography, a ciphertext where plain text is transformed into ciphertext using an algorithm. At the recipient end, the message is deciphered to recover the original end. Cryptanalysis used by an interceptor or an attacker on the ciphertext to determine the plain text information. So this all in my diagram. Implementing cryptography. Simplest arrangement rely on secrecy of the cryptographic algorithm. However, once it's discovered, all the information is insecure. It's a compromise. Okay. Security improved by using a key. DES, AES, RSA, they're all using keys. Okay. Constant algorithm, but produce different output depending on the key value. Okay. Key can be changed if compromise is suspected. Okay. Number of possible keys, key space. Problem with the key distribution requires secure protocol. Later we'll see all those things. Okay, basic cryptographic scheme, how it look like. We have plain text, the same my diagram. Plain text, we do encryption. Okay, E, we have ciphertext, we get the C, and then we do decryption, we get the plain text back. Okay, so this is how it look like. We have C, encryption for a P, same thing in the diagram. Okay, this one is a very basic XOR mechanism. Okay, immune to most cryptographic cryptanalytic attack. Okay, this one is XOR. Most of the algorithms still we are using this. Even what is that? OTP using XOR. Okay, so we have plain text, we have the key, some key, same key, then we get the ciphertext. P plus key, we get the ciphertext P plus K. Okay, so we combine this together, we get this one, and then we apply the same key, P, K, P plus K, we get the plain text back. Okay, P plus K plus K. Okay, we get the how? If we note that if same value, we get the minus. If same value, we get the minus. If anything change, we get the plus plus. For example, P is 110101 and K is 101010, and this is the key. So to get the ciphertext, we XOR these two, we get this value. Okay. How to get plain text back? This is the ciphertext. We get the same key. Okay, same key. We get this plain text back. Maybe later you can do this example by yourself. What are the benefits? It's just an improvement, but not a solution. After cryptography, we have authentication mechanism. Okay, each messages for authentication. If you go to online banking, so we write cmb.com.my, it will hit the server. The message need to be encrypted, and the message we receive from the server is encrypted. We only receive the message. I'm the user. I receive the one who request. Okay, but you see the authentication procedure is going on. So once we send the data, we receive the challenge. The challenge is encrypted. See, where is cryptography and authentication? Authentication have several encrypted messages. Okay, so you see from CIB Bank, enter your username. It's a challenge. If I am the legitimate, I enter my username. It's a part of authentication mechanism, but each message is encrypted. Okay, so alone encryption is not the solution. Okay, minimize problems doesn't solve them. Remember, there is no solution. Okay, this is all data. Adds an envelope encoding to an open postcard. Okay, clear text. So this one is benefits of cryptography. So we have very baseline techniques. One is transposition, how to apply, how to do encryption and decryption. Transposition, we have substitution method, and then we have concealment. See one by one. It's a transposition. Rearrangement of, okay, we go to this one. It's a plain text, make a secret. It's a plain text, simple transposition. How to encrypt? There must be, I think, there is a, never mind. So this S goes to E, E go to C, T go to this T, R go to S. So we transposition, we change the position. Okay. So encrypt, and then we get the ciphertext. Once we change the position, we get RTECSE. But to change, we cannot just randomly change. There must be some mechanism. We can say first go to last, second goes to second last, third goes to third last, R goes to third last. This is like this. We change the position, but some mechanism. Okay. Using matrix, you see, I love security subject. Okay, I love security. We put in the matrix. Okay, and then how to read ISIB, LETJ, OC. So this is now this word, this plain text change into ciphertext. This plain text change into ciphertext. But what we did, we just changed the position. Called this transposition. Very baseline method, but still applicable. If I'm using ABC and very critically but most of the system, if you go to ChatGPT, you write, some people use transposition. Can you help me to nanosecond? It will give you the. So that's why this all algorithms. If we have quantum computing, all current DES, AES, RSA, Diffie-Hellman, all will be broken. Okay, so this is transposition method. Then we have substitution method. Maybe later you people can read by yourself. Same thing, same thing. Okay, this is the key. We have ciphertext. How to get the cipher? We encrypt the plain text. CI at any instance. PI is a cipher and plain text. PI plus T. So we see this small green color is a plain text. So small, this one is a plain text. Okay, plain text plus 3. Plain text plus 3. 1, 2, 3 from here. Okay, so we change the ABC. We begin from after 3. A is equal to D, B is equal to E, C is equal to F, D. So S is equal to V. S is equal to V. E is equal to H. C is equal to F. So we put the value. Okay, we have some mechanism. This one is the key. We design this substitution method. We can do that. Small a, capital A, small b, capital B, small c, capital C, small d, capital D. But you see, it's a very simple method. So to make very minor complex, we just write this key. Okay, after 3, we change everything. Okay, so the secret message goes to this one. Okay, this is baseline algorithm. Concealment. Messages symbols are mixed up with many other symbols that carry no useful meanings. For instance, we have Adnan, A, D, and A, N. I just top up with P. A, P, D, P, N, P, A, P, N, P. So I add unnecessary character P after each symbol. Okay, so I try to hide Adnan. Okay. But what is the weakness is great considerable security, but can greatly expand the message, become a fat message. Okay, so this one is concealment. So these were our three very baseline algorithms, encryption method, encryption and decryption method. Okay, now we have Shannon rule. The amount of secrecy needed should be determined the amount of labor appropriate for encryption and decryption. For a banking system, you see we have OTP, we have biometric, we have authentication username and password. Okay, and then most of the time they say the password is not strong, the password is weak. Okay, so if the services have a value, it means high amount of secrecy is required. If we have high amount of secrecy, we must expect a high computational cost, high communication cost. Okay, for those things. The set of keys and the enciphered algorithm should be free from complexity. If we publish any article for cybersecurity, even for authentication mechanism, we have to prove that the algorithm is outperformed from complexity perspective as compared to baseline algorithm. So this is, we have to prove. If we don't produce our proof our complexity, the reviewers, they will send back, okay, can you please add on how complex is your algorithm. The implementation of the process should be as simple as possible. So this is for sure. Error in ciphering should not propagate. Sometime in the authentication request message, if we have some errors, it can go to authentication response message, then OTP, and then all authentication process. The error goes on and it end up with something. It causes corruption of further information in the message. The size of the ciphertext should not be larger than the plain text. That's why we have hash values, MD5, SHA, 256, all those we have 6 word, whatsoever word, we get a same amount of ciphertext. Okay. Now we have crypt analysis. Crypt analyst, the attacker, attempt to deduce the original meaning of the ciphertext. So this is the purpose. I need to see what's going on. Okay. So what are the goals? I need to make sure even the authentication request message sent to the CME bank break a single message, or even from the message came from CME bank as a response message, that single message. We try to break all those messages. Recognize the pattern in encrypted message to be able to break the subsequent ones. Okay, if we know the pattern, we know the first method authentication request message. The second is response, which have the challenge. Enter your username. Okay, and once we enter the username, the message have itself a challenge. Show me my secure word, so that we can prove that the server is legitimate server. Okay, and once the server show us a secure word, it give another challenge. If it is a sequence of messages, so it's easy to break up the subsequent one. Infer meanings without breaking encryption. Okay, so this is the goal. He need to make sure. Unusual volume of messages between enemy troops may indicate a coming attack. Busiest node may be we say this infer, we infer something. Busiest node may be enemy headquarter. Deduce the key. So once we know the key, the whole system is compromised to facilitate breaking subsequent message. Okay. Once we get the key, the things is done. Okay. Find weaknesses in implementation environmental of an encryption algorithm. This is his job. Find the weaknesses. Find a general weakness in an encryption algorithm. Not only the environment, but also the algorithm. Okay. Information used for cryptanalysis. Intercepted encrypted message, non-encryption algorithm, intercepted plain text. So these are the things that the attacker might need. Data known or suspected to be ciphertext, math or statistical tools and techniques, properties of natural languages, okay, to confuse the Japanese cryptanalysis American use Navajo language in WW2, okay, properties of computer system. So these are the things attacker need. Okay, we have classification of crypto system keys. There's some algorithm, they have keyless crypto system, that is less secure. And sometimes we have keyed crypto system. That is, we have two different symmetric crypto system where encryption and decryption keys are same. Classic using the same key. Asymmetric crypto system where encryption, decryption are different, just like our username and password. See, username is skadnan.unimas.my, that is my public key. Anybody can get it, I don't mind. But my private key is secure. So two different key. Okay, so that is asymmetric key. Breakable encryption. An encryption algorithm is called breakable. Give enough time and data. Analysts can determine the algorithm. Okay, so this is breakable and encryption. Okay, breakable encryption, practical crypto system almost always are breakable given adequate time and computing power. This is a universal truth. Requirements of crypto protocols. Messages should get to destination. So the crypto protocol authentication messages. Protocol means sets of instructions, sets of messages. Secure protocol for CIB bank, authentication request message, authentication response which is the challenge to the user, authentication response message to and response and give challenge to the server. Okay, we enter the, see, these are the sets of messages. Messages should get to the destination, one thing. Only the recipient should get it. Only the recipient should see it. Proof of the sender's identity. Message shouldn't be corrupted in between. Message should be sent, received once. Proof that the messages was sent, received, not. So these are the requirements, very baseline requirements, and everybody need it. Okay. How to make good ciphers? How to make good encryption? Cipher is encryption algorithm. Good cipher depend on intended application. Just like substitution, C hides character of P. So if it is greater than one key, C dissipates high frequency of characters. Okay. So this one is, it depends. Transposition, scrambled text hides n-gram of n. So this is one method. Product cipher can do all of what is more important for your application. If this one is, we need very high profile application, we need to make sure we scramble more. Okay. Okay. If it's high profile, we have to plan the key professionally. Okay. What facilities available for sender receiver? No supercomputer support on the battlefield. Okay, Shannon criteria. Needed a degree of secrecy should determine amount of labor. How long does the data need to be stay secret? Okay, set of keys and encryption algorithm should be free from complexity. Same thing. Same thing. Implementation as simple as possible. Propagation of the error should be limited, same thing. Size storage of C should be restricted. Okay, the size should not be, the ciphertext should not be bigger than the size of the plain text. Okay, confusion interceptor cannot predict what will happen to C when she changes one character in P. Okay. E with good confusion hides well relationship between P plus K and C. Diffusion changes in P spread out over many parts of the C. Okay. This one you can, it's a literature review, you can read by yourself. Commercial principle of sound encryption system, sound mathematics proven versus not proven so far. Okay. Verified by expert analysts. Most of the research articles in IDS, intrusion detection system, we need the expert to do the analysis, including outside experts, stood the test of time. Long-term success is not a guarantee. Okay, so these are some algorithms. Okay, now we have types of algorithm. We have symmetric algorithm, use a common secret key at sender and receiver end. Say common, same key, also known as a secret or private key cryptography. DES, IDA, example. Asymmetric algorithm uses a pair of keys, one secret and one public, also known as public key cryptography, RSA. Okay, this is example. We have sender, so we have ciphertext, we have encryption, the same key. See this yellow color key, we do the encryption. At the decryption point, we have decryption key. Okay, same key, we get the plain text back. This is symmetric key. Okay, asymmetric key, we have data. Encrypt using public key. Okay, and then we decrypt using private key. We get the decryption. Okay, so it look like safe. Symmetric key, it look like a safe. If we have Dropbox, maybe any okay, I have assignment and I make it password protected. Assignment PDF, password protected. I put in elib. Okay, so all my students need to use that file, but they need the password. Okay, if the password is ABC123 example, and then I send all my students ABC123, same password. Okay, I encrypt same password ABC123, you decrypt same password ABC123. Symmetric key encryption. But you see how to share the key. You're far away. Okay, how to share the key? One method. To get the key, everybody come to my room. I give you the keys. Okay, we call this key channel. If I post the key in, okay, suppose my students have different key. Okay, so very difficult to share. If I have 100, okay, I can share the key. I can generate 100 keys. But suppose if I have one base station have 65,535 users at a time. You see how to generate so much big key. We need random generator, random key generator. Okay, and then once we generate the key, we have to share the key. Share the key unicast, man to man. Okay, very difficult. 65,000 user, I give one by one key. At 1 nanosecond, give one. If we have 65, so maybe after 20 minutes, I get the OTP, suppose. Or I use the WhatsApp message, multicast. Attacker is there. So if a symmetric key is compromised, things are done. Okay, so you see the problem is how to share the key. The best way is to call you people to the office and give you the envelope. This is your key for the whole 1 week because key need to be changed. Okay, so 1 week, 2 week, 1 month, this is the key. If you receive any documents online, you have to use this key. So this is a problem with the private symmetric key. Ensuring security of the key channel. If I'm using WhatsApp, problem, the attacker is there. If I'm using eLeap, problem, the attacker is there. How to share the key? The best thing is to bring to the classroom and need an efficient key distribution infrastructure. A separate key needed for each communication. So if we need to have separate key, so we need to generate a lot of keys. So two problems. One is key channel, another is generate of the key. For n communication, user need n asterisk. You can see it. If it's 10, you can see how many keys we need. If we have 20, if we have 100 and we are 110 students, so you can see how many keys I need. Very difficult to generate the keys. For one base station at one time, 65,535 keys for 4 minutes. Everybody you apply for OTP. See, so how to generate those keys? Okay, so these are the problem. The first problem is key channel. How to share the key? What channel should I adopt? I should WhatsApp the students. I put in eLeap or face-to-face. And then there must be key distribution infrastructure. How to generate the key? Okay. For any communication user need this much keys. Okay, these are the problem with the symmetric. Asymmetric, we resolve the problem. I put the public key online and you generate your private key by your own. Okay, problem solved. Outlook 360, you register yourself and you get the public key. And then you have your own private key. Public key we can share. SK Adnan at Unimus, if you have, I don't mind. If you have my private, then private key, it's a critical situation. Public key encryption system eliminates symmetric key encryption problem. No need secure key distribution channel, easy key distribution. Even we have only 2 keys. No need to have so many keys. Here, for n communication, user needs so many keys, but here we have only 2 keys. Okay. One PK approach, key keeps R keeps her private key KT. Okay. Receiver can distribute the corresponding public key to anyone who want to send the encryption message to her. Okay, this one, let me, there's a diagram here. I will share. Can even post the key on an open website. It's public, as the name indicates, it's your public key, email address. Only private